Hello friends, welcome for the lectures on kinematics of fluids part 2. So in the earlier video in kinematics of fluid flow part 1, we have studied about the kinematics of fluid flow, methods of describing the fluid flow, types of fluid flow, and numerical graphical methods of the fluid flow analysis. So in this video, kinematics of fluid flow lecture, we are going to cover what is meant by discharge of the fluid flow, what is meant by continuity equation, and velocity and acceleration of the fluid flow, then velocity potential function, stream function, and simple equation used in the fluid flow analysis, that is Laplace equation. So first of all, we will discuss the rate of flow or discharge. So discharge, another name is rate of flow. So this is nothing but the quantity of a fluid flow flowing per second through a section of pipe or channel is called a rate of flow. For incompressible fluid flow, discharge is expressed in terms of volume of fluid flowing across the section per second. And for compressible fluid, the mass of fluid flow or weight of fluid flow flowing across the section. For liquids, the unit of discharge is meter cube per second or liter per second. And for gases, it is Newton per second, or sometimes it is expressed in terms of mass per second. So discharge is nothing but area of the flow, cross section of the pipe and velocity. So therefore, discharge is always considered as the Q is equal to A into V, where A is the area of the cross section of pipe and V is average velocity of flow across the section. Then in the fluid kinematics, very important equation is there. It is called as continuity equation. And this continuity equation is based on the principle of conservation of mass. So what is this principle of conservation of mass? The mass of flowing fluid per second is in a flowing fluid always remains constant. So if we consider this is a one pipe, cross pipe, and we'll consider two sections, section 1 and section 2. Then according to the principle of conservation of mass, the mass of flowing fluid at section 1 should be equal to mass of the flowing fluid flowing at section 2. And mass we can calculate by the equation. It is rho into area into velocity. So mass flow rate can be calculated by the formula rho AV, where rho is the density, area A is the area of cross section, and V is velocity. Now if you consider a fluid is flowing from this direction, left direction to right direction, and let us consider that the fluid is compressible or general compressible. So let us consider rho 1 is density of the fluid at section 1, A1 is the area of pipe at section 1, and V1 is average velocity of cross section at 1. And similarly, rho 2, V2 and A2 are the properties at section 2. Then as mass flow rate is given by equation rho AV, the rate of flow at section 1 is rho 1 A1 V1 and rate of flow is rho 2 A2 V2. And according to the conservation law, we say that rho 1 A1 V1 is equal to rho 2 A2 V2. But if we apply, this is going to be the continuity equation, can be applied for compressible flow as well as incompressible flow. But by the definition of incompressible fluids, the density of the flowing fluid always remains constant. That is, rho 1 is equal to rho 2, and therefore A1 V1 is equal to A2. So rho 1 rho 2 will get as and here the continuity equation will get for the incompressible fluid as a rho 1 A1 V1 is equal to A1 V1 is equal to A2 V2, because rho 1 is equal to rho 2. Then this continuity equation we have to derive in terms of differential form. So that is called next article we are going to cover. Then simple continuity equation is for incompressible fluid A1 V1 is equal to A2 V2, or discharge at section 1 is equal to discharge at section 2. Now here for continuity equation in 3 dimension, we are going to consider this particular element, a parallel piped element we are going to consider. So this is going to be one parallel piped element is there. So this is parallel pipe element. Now let us consider that this A, B, C, D, E, F, G, H is a parallel pipe element. Let us consider the x-axis. This is going to be z-axis, and this is going to be the y-axis. Let us consider U is a velocity component in x direction, V is velocity component in y direction, and W is velocity component in z direction. Okay, and let us consider that dx is the length in x direction, dy is the length in y direction, and dz is length in z direction. Now here we know that the mass of flowing fluid is given by equation rho into area into velocity. Now let us consider calculate the mass flow rate entering at section A, B, C, D. So this is going to be A, B, C, D. A, B, C, D. So this is going to be entering section and leaving section is E, F, G, H. Let us consider that the mass entering at the face ABCD is equal to rho u, velocity component in x direction is u, density is rho, and the area of cross section is equal to here. For example, this is a dy is there and dz x component. So area cross section area will be dy BC length and CD length dy into dz. Then it is equal to rho into u into dy dz. Okay. Then the mass of living phase EFGA. So this phase after some time EFGH phase, the mass will leave. So this mass is equal to, mathematically we can say that this mass is equal to, here is equal to change entering mass AU, that is rho u divided plus there is going to be some mass is going to be changed along that x direction, and we say that dab of dab by x is going to be a small change in mass, and then dou of dou x is going to be a small change in mass rho u divided, but the entire length for x section for that particular when the fluid is traveling in x direction is dx. So therefore the mass of fluid leaving EFGH is equal to the original mass flowing is rho u divided dz plus dou of dou x rho u divided dz into dx. So this is going to be the mass flowing in the x leaving the phase EFGH. And how much mass is gained in the x direction? So leaving mass, it is going to be the mass entering ABCD minus mass leaving EFGH. So therefore it is going to be rho u divided minus rho u divided minus dou. So it will become here the mass entering gained mass in x direction is minus dou by dou x into rho u dy dx dy dz. So rho u is going to be the here dx dy dz is going to be the length and they are constant, therefore we can take outside the bracket. So minus dou of dou x rho u dx dy dz is going to be the gain in mass in x direction. Similarly the gain in y direction is equal to minus dou of dou y rho v du dx dy dz. Similarly, if we apply the same principle, then the mass gain in x z direction is minus dou of dou z rho w dx dy dz, and net gain is equal to gain in x direction plus gain in y direction plus gain in z direction, and therefore it is equal to dou of dou x rho u plus dou of dou x rho v plus dou of dou z rho w into dx dy dz, and minus sign is there. Okay, and this is going to be gain. Now this gain in mass is also can be calculated by the change in density of that element, and it is given by the equation d rho of dt in that time period, d rho of dt into dx dy dz. So mass is changed, therefore density is going to be changed, therefore this is going to be gained mass is also can be expressed in terms of change in density, as density is changing, dou rho by dou t is equal to change in density, and therefore these two equations are there, these equations were equate. Therefore if you gain net gain is equal to net change mass in that term, and if you go in that way, and let us consider now the fluid is incompressible. So or we can say that dou of dou x rho u plus dou of dou y rho v plus dou of dou, if this minus sign will take this side, plus dou of dou z rho w plus dou rho of dou t dx dy dz is equal to 0. Okay, or if dx dy will cancel. So dou of dou x plus dou of dou y rho v plus dou of dou z rho w plus dou rho of dt is equal to 0. Then this, if you consider that fluid is incompressible, there in that case this rho we can take outside and is equal to 0 will be get cancelled. Therefore what we can say, d rho of dou rho of dt plus dou of dou x rho u. So this is going to be equation we can consider is a general form of the continuity equation, is applicable for steady flow as well as unsteady flow, uniform as well as non-uniform flow, compressible as well as incompressible fluids. Now let us consider that rho incompressible fluid rho is going to be constant, and therefore for incompressible flow, three-dimensional flow, the continuity equation is become dou u of dou x plus dou v by dou y plus dou w of dou z is equal to 0. For two-dimensional case, dou w of dou z will cancel, dou u of dou z dou x plus dou v of dou y is equal to 0. Then velocity components we have to calculate. Let us say v is a resultant velocity in a fluid flow and u, v, w are the velocity components. So here u is a function of x, y, z because three-dimensional flow. F1 of x, three space coordinates x, y, z and time. V is another function of x, y, z, t. W is F3 of x, y, z, t. And in that case, resultant velocity v is equal to, velocity vector is given by ui plus vj plus wk, where I, j, k are the unit vectors in x direction, y direction and z direction. And resultant velocity we can calculate in the magnitude, that is square root of u square plus v square plus w square. Okay. Similarly, we have to calculate the accelerations component in x direction, y direction and z direction. And for that, we have to use the chain rule of differentiation. So here, x is equal to du by dt, but u is a function of x, y, z. Partially, u is a partially function of x, partially function of y, and partially function of z, and partially function of t. Therefore, this du by dt we have to calculate with the help of chain rule of differentiation, and is equal to what? Here is equal to now dou u by dou x plus dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt and plus dou u by dt into dt by dt, but dt by dt will get cancelled. Therefore, here dx by dt, but we know that dx by dt is equal to change of displacement per unit time and is equal to velocity, and that velocity in x direction is u, y direction is v, and z direction dw. Therefore, dx by dt is equal to u, dy by dt is equal to v, and dz by dt is equal to w. Therefore, x will become as du by dt is equal to u into, this is u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dt. Similarly, ay is equal to dv by dt is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou u by dou z plus dou v by dou t. Similarly, dw by dt, dz is equal to u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. For steady flow, this dou u by dou t, dv by dou v by dou t, dou w by dou t will become 0. So this way, then resultant acceleration is equal to, again is the acceleration vector is equal to what? Here ax is equal to axi plus ayj plus azk, and therefore resultant vector also is going to be resultant due to ax square plus ay square plus az square. Then local acceleration and convective acceleration are the types of acceleration. So local acceleration is defined as the rate of increase of velocity with respect to time. So those components are there with respect to time. Dou u by dou t, then dou v by dou t, dou w by dou t are the local acceleration terms. And convective acceleration terms are the terms where the velocity changes is with respect to space only. So acceleration component only due to space is nothing but dou u by dou x, dou u by dou y, dou u by dou z. So these are the acceleration terms. And resultant acceleration is always sum of local acceleration and convective acceleration. Then there are some important terminology we have to use for the kinematics of fluid flow. That properties we have to calculate. When velocity vector we know, all this property we have to calculate. So one of the kinematical term is their velocity potential function. So these are all terms are mathematical terms, and these terms velocity potential function is defined as the scalar function of space and time such that its negative partial derivative with any direction gives fluid component in that direction. It is negative velocity component. So phi is, it is denoted by letter phi, denoted by letter phi, and phi is the function of what? X, y, z, and t. Okay. Now here we can say that here velocity component in any direction gives its negative partial derivative with respect to any direction gives velocity component in that direction. So we know that u is velocity component in x direction, v is velocity component in y direction, and w is velocity component in z direction. So here therefore u is equal to minus dou phi by dou x, v is equal to dou phi minus dou phi by dou y, and u is equal to minus dou phi by dou z. And in cylindrical polar coordinates, ur is equal to dou phi by dou r, and u theta is equal to tangential component, u theta is equal to 1 upon r d dou phi by dou theta. So negative partial derivative with respect to any direction gives velocity component in that direction. So v is equal to minus dou phi by dou x. Here we have to remember always v is equal to minus dou phi by dou y, and w is equal to minus dou phi by dou z. Similarly, there is another function is called as potential stream function. What is stream function? The stream function is also a mathematical function. It is a scalar function of space and time such that partial derivative, no negative, partial derivative with respect to any direction, partial derivative with respect to any direction gives velocity component right angle to that direction. So it is a two-dimensional function. If you want to calculate the velocity vector, velocity in x direction, and we have to differentiate this psi, and you denote by letter psi, okay, psi, and this psi we have to differentiate. So to get the velocity vector in x direction, here we have to differentiate this psi with respect to y. So dou psi by dou x is equal to minus u. And this minus and plus sign is different according to the what streamline we are taking. So Bansal book they have taken dou psi by dou y is equal to minus u, and dou psi by dou x is equal to v. Okay, so this is going to be stream function. That is, it is a scalar function of space and time. The such that partial derivative with respect to any direction gives velocity component in right angle to that direction. For example, v is equal to get v, we have to differentiate psi with respect to x, and to get u, we have to differentiate psi with respect to y. And negative u and 1 is positive. It depends on the scalar streamline. Both may be negative, both may be positive. Okay, or maybe v may be negative or u may be negative. But whatever that author has taken streamline, depending on direction is there. And now last thing is their Laplace equation. So Laplace equation we know that here dou u by dou x plus here Laplace equation dou u by dou x is continuity equation we know dou u by dou x plus dou v by dou z dou v by dou y plus dou w by dou z is equal to 0. If you put u in terms of that is dou minus dou phi by dou x, v is minus dou phi by dou y minus dou phi by dou z, dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. So this is called as Laplace equation. Dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. This is called as what? Laplace equation. Okay, so in this way we have completed the analytic part of this particular chapter. Okay, so this completes our unit number 2, that is fluid kinematics or kinematics of fluid flow. Thank you very much.